All right, I want to start by just taking a look at this opening problem, and I'd like for you to pause and take a look and try to answer these first three questions. So my curve is shown on the right, and we want to think about which points is the tangent horizontal, right? So hopefully you recognize that was at points B and D. We have my horizontal tangents. The function is increasing. That's going to mean as I go rightward, when is it going upward, right? That's what I mean by increasing. If it's going rightward, when is it going upward? So you'll notice this piece is going upward all the way. So maybe you said before B, and then again after D, right? This piece, they're going upward as well, right? Versus when is it decreasing means as I go rightward, when is it going downward? So maybe you said between B and D. And then when does the curve change its shape? That's going to mean when does it go from kind of the way I've referred to it before as looking like this hill to when does it start to look like this bowl instead. So I'm going to say at point C, it's what I call changes its shape. So this whole chapter 16 is going to be analyzing the graphs of functions, analyzing the curves using my derivatives. Right, so we're going to use derivatives to analyze the graphs. And then when we move to chapter 17, we're going to apply those to real-world problems, as I've kind of mentioned, displacement and velocity and acceleration. So the first section here is on tangents and normals. Thankfully, you know what a tangent is, right? A tangent is a line that touches the curve at a specific point, but even more so than that, we talked about like this touches, ha ha ha. But we really mean is touching at a unique point, and it doesn't cross through it most of the time. And really, the true calculus definition says that the tangent to a curve, or the tangent line to a curve, is the limiting line of the secant lines, right? So the tangent or tangent line is what we call the limiting line of the secant lines. So chapter 14, last trimester, you drew secants from a point to that A, and then from this point to that A, and from this point to that A, and we said the limit is this to that A, is that just touching, and you did the same thing from this side and drew a secant, and then the secant, and then the secant, and they all approach this line. Since the limit was the same on both sides, we said this was my tangent line, right? The gradient of the tangent at that point, right, the gradient or slope, right, the gradient of the tangent is the derivative of the function at that point, right? That's what we define the derivative function. The slope of the tangent is the derivative at this point, so in this case at point A. Now we have a new definition for a new function we're going to have as well, right? Oops, that was the erase. Is the new line, The normal to a curve, or the normal line to a curve, is the line which is perpendicular to the tangent at that point of contact. So my same point here, this is the normal line. It's perpendicular to my tangent, that green line you see in there. It's perpendicular to my tangent here at that point, specifically at point A. So in a similar way to the fact that my tangent line is going to look different at different values, for example, right, my tangent down here is going to look like this, right, touch that there. The normal is going to look like this, right? It's perpendicular to that tangent line. So the slope of the tangent to my curve is the derivative at that point, right? That's what we call the slope of the tangent. Slope, we tend to use m. I'm going to call it m sub t, standing for tangent, right? The tangent. Tangent. The slope of the normal then, and hopefully you remember from back in the day, the slope for a perpendicular line is going to mean the opposite reciprocal at that same point. So the opposite reciprocal is the slope of the normal. So I use the subscript n for the normal. Right? The normal has a slope of the opposite reciprocal to the tangent slope, because that's of course going to mean perpendicular. So let's look at a couple examples to do that. We're going to be writing equations. We're going to fill in this here in a moment, right? We know that the slope, let's just use a different color since we're doing totally different things, that the slope is, of course, change in y or change in x, right? And that's where point slope form actually comes from. If I multiply both sides by my x2 minus x1, I end up with m times x2 minus x1 equals y2 minus y1. And if I just don't call this an x2, I just call it an x, that's the point slope form. Typically, we see it written on this side, right? But keep in mind, this is the ordered pair, x, y, and then, of course, I have my slope, which then means that for my tangent, my function is y minus my y coordinate at that point, the f of a, and then I say my slope and x minus the a, right? This is actually the same for both. The slope for a tangent is the derivative at that point, right? Versus a normal is still y minus my y coordinate, and then slope times x minus my x coordinate. The slope here is the opposite reciprocal of the derivative. So be careful that this is derivative and this is just function. Right, this is derivative and this is just function.